What we're going to do now is to take the sigma point approach to being able to propagate some uncertainty, random variable uncertainty, through a nonlinear function, and we're going to apply that to the state estimation problem inside of a Kalman filter. Now what we said before was, suppose I've got some nonlinear function and I had a random variable x as input that produced a random variable y at the output. I would make sigma points to represent x. I would pass those sigma points through the function to get sigma points to represent y. We encounter a complication when we look at the Kalman filter model equations, because there are multiple inputs to the nonlinear functions that are each themselves random. So it's not just a function of x, the state, it's also a function of w, the process noise, and v, the sensor noise. To use the sigma point approach, we need to jointly model all randomness. We need to make basically one set of sigma points to model them all, and this set of sigma points jointly combines the randomness, the uncertainty of the state, the process noise, and the sensor. So instead of having a state x that we talk about, we're going to have an augmented state xa that combines the randomness of the state itself and the randomness of the process and sensor noises. That's really the biggest complicating factor. If we can get beyond that, the rest of the sigma point Kalman filter is going to actually be quite straightforward. So step 1a, we're going to go through the 6 steps of probabilistic inference and use those with a sigma point approach to come up with a sigma point Kalman filter. And what we want to do is we want to find the predicted state, which means I have to take the random information from the previous time step, the state estimate, the state covariance at the previous time step, and propagate that through the nonlinear function that is the state equation of the model to get a prediction of the state right now. We're going to start by making a bunch of sigma points that describe the randomness of the state estimate error from the previous time interval and the process noise and the sensor noise. The mean of this augmented vector is going to be the estimate of the state at the prior time, the mean process noise, the mean sensor noise. Of course, that's all a vertical vector, hence those transposes to show that. The augmented covariance matrix, assuming that there's no correlation between the process noise now and the state then, and the sensor noise now and the state then, there should not be, is a block diagonal matrix where the top left is the covariance of the state estimate at the prior step, then I've got the covariance of the process noise, then the covariance of the sensor noise. Using these large augmented state and covariance matrices, we generate augmented sigma points. And so it's script x augmented, hence the a, relating to time k minus 1, hence the k minus 1, and the estimate, not the prediction at time k minus 1, hence the plus. The equation for describing this is the same as what we've seen for regular sigma points. So the mean plus gamma times Cholesky factor, and mean minus gamma times Cholesky factor. I drew a picture that I hope helps illustrate how we're making these augmented sigma points. Here, I start out with the augmented mean, where the top elements here, I've drawn 4 state elements from the previous time step. That's just an output from the previous time step. And then W bar and V bar. And in this example, I've got 4 states and 2 process noise states, or well, not states, but inputs, and 1 sensor noise input. So I've got 4, 2, and 1 vertically. And then the augmented covariance matrix over here, where this part is sigma x tilde k minus 1 plus. Actually, that's indicated by that label right there. And then the next part is the sigma w, and the next part is the sigma v, and the parts that are not shaded, the parts that are white, are all 0. So that's the input to creating sigma points. Then we take the Cholesky decomposition of all of this to get a lower triangular matrix of all of that, and the structure of the Cholesky would just have numbers there and there and there and there and there, and I think possibly even there and there and there. Although, no, I'm going to change my mind. Those are 0, so it's just there, there, and there. So the white part is still 0, but the part that used to be green, of different shades of green, is now a lower triangular replacement because I'm doing the Cholesky factor of that. Okay, and then we do the same process as we did before. So we take the overall augmented mean and we stick that there, and then we take the mean in the first column, so gamma times the first column, and we stick that there, second column, stick that there, and so forth, and we make this fairly large matrix of augmented sigma points. And the shading is done to try to show, okay, I've got light blue, medium blue, dark blue, and I've got light green, medium green, dark green. The light is always with the state, the medium is always with the process noise, and the dark is always with the sensor noise. So looking this way in this matrix, I see 2 times L plus 1, where L is the size of the augmented vector. So 2L plus 1 sigma points. Each column is itself a sigma point. But then looking this way, we see that each row of the augmented sigma point also has a meaning. So the top 4 rows have to do with variability of the state in my overall uncertain thing. The next 2 rows have to do with variability of the process noise, and the last row has to do with variability of the sensor noise in my overall augmented joint uncertain variable modeling. So thinking about it that way, what we're going to do next is we're going to take the augmented sigma points and we're going to split them into 3 sections, just vertically. So the top points are what we're going to call the sigma points of the state at the previous time step estimate. So k minus 1 previous plus is estimate. And the superscript x says these are the sigma points having to do with the state. And then the sigma points having to do with the process noise w, hence superscript w, and the sigma points having to do with the sensor noise, hence the v. So we'll split them apart into those 3 sections. So now we have sigma points that describe what's happening right before step 1a, and I'm going to use these sigma points to form a prediction of where I think the state is right now, in order to implement step 1a. What we're going to do is we're going to evaluate the state equation, F, using all pairs of sigma points for the state and sigma points for the process noise, where this additional subscript I denotes the ith sigma point, the ith vector extracted from this set. And when I do this, this is going to give me a set of sigma points x minus. I start with x plus from the previous time, and I end up with x minus for the present time. Mathematically, we could write this. It says that the ith x minus sigma point is obtained by taking my state equation and evaluating it with the input of the ith x plus sigma point and the ith w sigma point and the deterministic input u. The picture may help illustrate that. So I've redrawn the x plus sigma points from the previous time and the xw sigma points, the w plus sigma points, and I take them a column at a time, and that's what I mean by pair. So a column at a time here. I stick them into the nonlinear function. I stick in the, maybe I should have pointed a little differently. I'm just trying to show that they go into the state equation block, but the x goes into the x, and the u, which is the deterministic measured input, goes into the u, and the w goes into the w over there, one at a time, and that produces a corresponding output to those inputs. So in this case, I think L was something like 7, so I had 15 sigma points. So there's going to be 15 output sigma points, which are the x minus sigma points. That's just all introduction. What I really need to do, remember step 1a of general probabilistic inference says compute expected value of the nonlinear function given the all of the measurements up until the previous point in time. We say, well, we're going to do that by propagating sigma points through my nonlinear function that represent the state at the previous time and the process noise. We're going to do a weighting of those using the mean value weights, sum all those up. So I sum all of these up weightedly, and that gives me my prediction x hat k minus. And we could write that then here, because these function evaluations we called script x, superscript x minus. We could write it that way. That's all we're doing. We're taking data representing what we know about uncertainty going into the state equation. We're putting that into the state equation. We're getting data out, and we're finding the weighted mean of that data. That is my state estimate. Now this can be computed using a fairly simple matrix multiply operation. If I take all of my output sigma points organized as a matrix, and I organize my weights as a column vector, and I multiply on the right by that, that does all of the summing and the weighting for me. So this entire summation can be computed in MATLAB quite compactly and efficiently by doing this matrix times vector product to give me x hat k minus. That's step 1a, and it's by far the hardest step to describe because there's some new concepts there. Step 1b is the covariance. I do this covariance calculation. I've already computed this. I subtract that from every sigma point. I do this weighted sum, and that gives me the covariance. Step 1c, I estimate the system output. Again, I'm faced with a nonlinear function. I want to know the mean and the variance at the output of this function given the mean and the variances of the input to this function, so I use the sigma points. I take the inputs, so what I need to do is I need to say the nonlinear function h has inputs corresponding to x hat k minus, so I take the sigma points describing x hat k minus, which was the output of step 1a, or an intermediate part of step 1a, and I take the sigma points that describe the sensor noise. Again, we computed those sigma points in 1a, put them through the output equation pairwise, one at a time, to get the output sigma points that represent the output. So here I've got the sigma points corresponding to the sensor noise from the very first step, from the augmented sigma points, and then from the output or intermediate calculation in step 1a, I've got these sigma points also. I take them a pair at a time, and I put them through this function. So the state part goes through there, the noise part goes through there, and the known u is also put into the function. And then that computes a corresponding output sigma point. So these would make an output there, and obviously the ones drawn make an output there. So I end up with, again, 2L plus 1 output sigma points. We do that because I'm trying to compute an estimate of the expected value of the nonlinear output function of x, u, and v And I did that by passing sigma points through the function representing my uncertainty of the state and the sensor noise, and I do the weighted sum of those output data points to get y hat. And this can be done using a simple matrix multiplication, as we did when we calculated x hat minus at the end of step 1a. Now we compute the gain matrix of the estimator. And to do that, I'm going to need a sigma y tilde. Well, that's in the sigma point way of thinking about things. I take sigma point representing y minus the mean and sigma point representing y minus the mean, and we do the statistical weighted covariance calculation of that. And then the cross covariance between x and y, I take the sigma point representing x minus its mean and the corresponding sigma point representing y and its mean, and I do the weighted calculation involving that, and that gives me those matrices. And that's enough to compute the Kalman gain, which is simply this. Then step 2b is unchanged for any Kalman filter. It says prediction plus L times measurement minus prediction equals estimate of state. That is my output of the SPKF at this time step, and the error covariance is the prediction covariance minus L times the output covariance times L transpose gives me the updated estimate covariance. So the output of this filter, same as any other Kalman filter, these things there. The steps required to obtain those outputs are a little different from any other thing we've seen so far, but it's just carefully applying the sigma point approach to modeling nonlinear function output uncertainty given nonlinear function input uncertainty.